All right, so we have seen digital signature algorithm, but I already mentioned that it is not the signature algorithm that is used in cryptocurrencies or blockchains. So most of the time we use elliptic curve digital signature algorithm because Bitcoin uses it, and almost every following alternative currency use the same library with Bitcoin and use the same elliptic curve. So this is why elliptic curve digital signature algorithm is very important when you work on blockchains or cryptocurrencies. So elliptic curve digital signature algorithm, ECDSA is short, is the elliptic curve analog of the digital signature algorithm. So if you know the digital signature algorithm, you simply change the group operations to elliptic curve operations. That's it. That's the whole difference. So this was proposed first in 1992 by Scott Vanstone in response to NIST's request for public comments on their first proposal for DSS, digital signature standard. So it was accepted in 1998 as an ISA standard. Also, Americans followed 1 year later. And in 2000, it became an IEEE standard. But, in the last 2 decades, it was included in almost every standard related to signature. So this is like the, most used signature algorithm so far. So let's start with this same thing with what we did with digital signature algorithm. Recall that there we started with choosing domain parameters. Here, our domain parameters are different because now we need to agree on an elliptic curve and the fields and so on. So the domain parameters for ECDSA consist of a suitably chosen elliptic curve E defined over a finite field FQ of characteristic P. So I say the suitably chosen because there are some cryptanalytic attacks. So in order to avoid this, there are some rules that you need to follow. So you cannot use every elliptic curve, okay? So here we are working on FQ of characteristic P. This means that Q might be something like P to the power something. Recall that a field can be either of prime elements, like FP, or prime powers. Okay. Another domain parameter is the base point G, which is an element on the elliptic curve over FQ. Okay. Domain parameters may either be shared by a group of entities or specific to a single user. So the first type is what actually cryptocurrencies use. So in Bitcoin, for instance, we have the domain parameters. We know the elliptic curve, the generator point. So every user that uses Bitcoin actually uses these parameters. Okay. So let's look at how these parameters are chosen. First, you choose the field size, Q. Again, Q can be either a prime number or, it can be a power of 2. This is what we use in practice. I mean, it can be also power of 3, which is also prime. But again, this is not what we use in standard. So an indication, field representation of the representation used for the elements FQ. Since this is a field, you have to decide how you represent the elements, right? So this is why you should indicate it with FR. Optionally, if you randomly generated this elliptic curve, probably you use the seed value, so you have to include it here, okay? If it is, randomly generated. If it is not, if you're taking this elliptic curve from a standard, and you don't need to have the seed value. So two field elements A and B in FQ, which define the equation of the elliptic curve E over FQ. Recall that we defined the elliptic curve as y squared equals to x cubed plus ax plus b, if we are working on prime fields. Or if it is a power of 2, we define it like this, But in both cases, we have two field elements A, B here. So you have to choose that because that actually specifies which elliptic curve you are using, okay? So two field elements, X and Y. These are, so actually this means that you actually have a point here whose coordinates are in FQ, and it should be of prime order in here. So this point should generate elements of number as a prime, right? This is what prime order means. So you add to G to itself, you will obtain different elements, but the number of elements it generates should be of prime number. The order n of the point G with n equals to 2 to n is larger than 2 to 256, and n is larger than 4 times square root of q. As you can see, these are some precautions that we need to make so that it is secure. If you choose n really small, then here I say 256 due to the polar true algorithm, because this way it provides at least 128-bit security. Okay. We also define h, which is the cofactor, and it is defined as number of points on the elliptic curve divided by n, which is the order of this g. All of these values are your domain parameters. So in the Bitcoin, you say that these are the domain parameters, and this is why we use it. So initially, you have to decide all of these so that you can use this elliptic curve and the points there. Okay. So it looks a little bit more than the digital signature algorithm, but to be in short, you agree on the field. Okay. You agree on an elliptic curve, so you choose A and B's to define that elliptic curve. Then you choose a prime order point on that elliptic curve. That is the thing that you need to do. Actually. Now let's look at the key pairs. An elliptic curve digital signature algorithm key pair is associated with a particular set of elliptic curve domain parameters, which we explained in the previous slide. The public key is a random multiple of the base points, while the private key is the integer used to generate the multiple. Your idea is as simple. You randomly choose an integer, say d. You add the point g to itself d many times, and the resulting point will be your public key. So an entity A's key pair is associated with a particular set of elliptic curve domain parameters. These are all of the values that I explained in the previous slide. A and B determines the elliptic curve, Q is the field size, G is the base point, and so on and so on. FR is the representation, field representation, and so on. This association can be assured cryptographically, for example, with certificates, or by context. For example, all entities use the same domain parameters. So this is what we do in Bitcoin. So by context, we know the domain parameters. Okay, but if you don't know them, you have to, either look at the certificates, or otherwise you have to verify it. This is very important. The entity A must have the assurance that the domain parameters are valid prior to key generation. So this is really important. You might think that this is just an unnecessary sentence I added at the end of the slide, but it is really important. So when you want to communicate with somebody, either using Elgamal encryption or anything, but you are using elliptic curve, so you need to know the domain parameters. And if somebody sends you the domain parameters, before checking, creating keys or validating signatures, you have to check if those parameters are correct. So I'm saying this because we said this in all of our papers, that this is what you do in practice. So at some point, somebody who is implementing these algorithms might think that this sentence is unimportant, so they may not check the domain parameters. So this is what happened last year when I was teaching. This has happened in OpenSSL. So it turned out that they are not verifying the domain parameters. So this way, you can actually give wrong domain parameters, which doesn't actually generate an elliptic curve or anything. So since they don't verify it, they try to verify the signature in the OpenSSL, but this actually causes an infinite loop in the mod square root function. So this way, you can actually perform a denial of service attack by sending wrong parameters to any OpenSSL server with this way. Okay. So let me explain what it is. The bn mod square root function, which computes a modular square root, contains a bug that can cause it to loop forever for non-prime moduli. So this is the thing, if your domain parameters are not correct, then it will be a non-prime modulus. So this will create an infinite loop. Internally, this function is used when parsing certificates that contain elliptic curve public keys in compressed form or explicit elliptic curve parameters with a base point encoded in compressed form. It is possible to trigger the infinite loop by crafting a certificate that has invalid explicit curve parameters. Since certificate parsing happens prior to verification of the certificate signature, any process that parses an external supplied certificate may thus be subject to a denial of service attack. The infinite loop can be reached when parsing crafted private keys as they can contain explicit elliptic curve parameters. So this is what happens to a server. You send a certificate with elliptic curve domain parameters or your keys, and there you actually use wrong parameters. And you know, the server runs this function, but it goes into an infinite loop. So you're actually exhausting the server because they're running their CPU cycles for unnecessary stuff. So vulnerable situations include TLS clients consuming server certificates. So you're a consumer, a server sends you a certificate, and you know this bug happens. So here I will list when this vulnerability occurs, and you will realize that it can always happen. TLS server consuming client certificates, so you can attack servers. Hosting providers taking certificates or private keys from customers. Certificate authorities parsing certification requests from subscribers. Anything else which parses ASN1 elliptic curve parameters. Also, any other application that use this function where the attacker can control the parameter values are vulnerable to denial of service issue. So a simple mistake, a simple, you know, you don't just write, all they need to write, you know, a if clause where you just check the domain parameters. And somebody just said that, okay, this line is unnecessary, let's not use it. So this is what happens when you don't listen to precautions of the cryptographers. Okay. Now we created the domain parameters. Now let's move on to key pair generation. Each entity A does the following. So you can, by each entity A, you can think about them any Ethereum or Bitcoin user. Okay. You select a random or pseudo-random integer D in the interval 1 to n-1. So this is sometimes might be a problem because maybe somebody, since you are allowed to choose it by yourself, somebody might choose it as a very small number, right? They can choose D equals to 3. So you can actually go to any cryptocurrency like Bitcoin and Ethereum, and you can, try brute force attacks to check if somebody used a small D or non-random D. So if you can guess how they generated this D, you can actually guess it. And D is your private key. So this is why it is important. So once you choose your private key like this, you actually add G to itself D many times and obtain a point on the elliptic curve. Here, it looks like a multiplication, and sometimes people say that this is point multiplication, but it is not. This is a scalar multiplication. Not that important, but I want to, correct the literature just by saying this. Okay, this is not a point multiplication because you are not multiplying 2 points. You are multiplying a point with a scalar. So this means that you are adding that point to itself D many times. Okay, so here D is not a point on the elliptic curve. D is just an integer, but capital G and Q are points on the elliptic curve. So a public key, A's public key is Q, private key is D. As you can see, this is where the discrete logarithm comes into play, right? D is your secret key, and everybody knows G, and you provide Q when you make a transaction, or you say that this is my wallet address. Otherwise, people don't know your Q. But somebody knowing Q and G cannot capture D due to the elliptic curve discrete logarithm problem. Okay, it is hard. So whole security lies here. So let's move on to signing and verification phases, which is almost identical to digital signature algorithm, but the operations are no longer on ZP, but on elliptic curves, okay? So we want to sign a message M. This means that I'm actually sending Bitcoin to somebody, okay? This message is the transaction I'm doing. So, or Ethereum, I want to sign it as the entity A, okay? So the domain parameters are the same for Bitcoin and Ethereum. It's specified. I showed you last week, but I will show it again. And associated key pair is D and Q. So D is your secret key, private key. You will use it to sign it. And Q will be your public key. People will use it to, verify your signature. So start again. You randomly select an integer K. As I mentioned again, in the DSA, if you use the same integer k twice for signing two different messages, due to some, number theory, we can actually capture D from there. Again, this happened. I don't know if I included in the slides, but people stole more than a few Bitcoins this way. Okay, first talk about the signing phase. So I choose a random integer k. I compute kg, so I add the base point to itself k many times. So I obtain the coordinates. But since these are field elements, I should represent them as an integer. So I should choose a way to represent it. And there's a very simple transformation here. And this is explained in the ANSYS standard, so nothing that important, okay? But since we are moving from field elements to integers, you have to make a, proper conversion. So these bars actually represent integers, okay? So now I compute R, which is x1 mod n. If R equals to 0, then go to step 1, okay? This is again important, by the way. You have to write in, when you implement this, you have to check if R equals to 0, okay? People didn't do it again in Java at some point, so there was a point where you can provide blank signatures where Java thinks that it is valid, okay? Compute K inverse modulo n, again, use extended Euclidean algorithm. Calculate the hash of your message or transaction, and convert this bit string into an integer, E, okay? So this is you converted your hash into an integer E. Compute again, as you can see, this is very similar to the DSA algorithm. Here D is your secret private key, right? So here is the step how you sign it. So you obtain S. Again, if S equals to 0, this is not acceptable. You go to step 1, choose another random key, and perform these steps again and again. But at the end, if R and S is different than 0, a signature for the message M is R and S. So this is important. This is actually what you're writing to blockchain when you perform a transaction on Bitcoin or Ethereum, okay? This is why it is important. M is your transaction. R and S is the signature for that transaction. So whenever you announce a transaction in the Bitcoin or Ethereum or any cryptocurrency, each node actually checks if this transaction is okay, if the signature is correct. If the signature is correct, then if you are a miner, actually the pool verifies that the signature is correct, then it gives the miners this transaction so that they can include it in the mining process. Okay, let's move on to signature verification. To verify A signature RS on the message M, B obtains an authentic copy of A's domain parameters. Again, in Bitcoin and Ethereum, everybody already knows these domain parameters because we are using a specific one. And associated public key Q, okay? It is recommended that B also validates D and Q. Again, this validation here is also important. If you don't do it, a denial of service attack that happened in OpenSSL can also happen to you. If the parameters are correct, if you obtain the signature, B then does the following. Verify that R and S are integers in the interval. Compute the hash of the message and convert it into an integer. Compute S inverse. Again, S is coming from the signature. You compute, multiply with W. Again, this is what we did on the digital signature algorithm. At this point, as you can see, this is where things are different. Now I'm performing group operation. I'm adding point G to itself U1 times, Q to itself U2 times, and obtain a point on the elliptic curve X. Now I check. If X is the point of infinity, then I reject the signature. Otherwise, I convert the X coordinate of this point, X1, convert it into an integer, X1, and then compute X1 mod N, so obtain V. I check if V equals to R, which is again coming from the signature. Okay. Very similar to digital signature algorithm, but instead of field operations, we performed operations on the points of elliptic curve. So it might be surprising, but this is what happens whenever somebody makes a Bitcoin or Ethereum or any cryptocurrency transaction. This is how you sign it, okay? Of course, nowadays, it also supports Schnorr signatures, which we will cover in the next week, okay? Proof of the signature verification works. If a signature RS on message and was indeed generated by A, then, S equals to this. Rearranging the keys, if you actually multiply both sides with S inverse and that kind of thing, you just, do the same stuff that we did before. At the end, the secret key is, actually turns this G to, the one U1 and U2 that you calculated. Okay. So I'm not going much into detail because we have to follow every step, but I want to, leave it to you so that to see that it really works.